In this screencast, we're going to learn how to do optimization, which is finding the maximum or minimum values for different situations through a technique known as linear programming. Let's jump right in with some terminology involving linear programming. So linear programming itself is a process for optimizing, that is, finding the minimum or maximum, the best value something can be in a situation given certain constraints. So optimizing is to make something its best. And usually that involves, in terms of a quantity, either minimizing or maximizing it. An objective function is the thing we want to optimize, the thing we want to make a maximum or a minimum. And it's expressed as a function of usually two variables in these kind of situations. Constraints are the facts in the situation. They are usually expressed as linear inequalities of the same variables, things that are going to help define the situation that needs to be optimized. The feasible region is the polygon we get when we plot the system of linear inequalities that are known as the constraints. The solution to those is known as the feasible region. The corner points of those, which are also known as vertices, the corner points of this polygon are critical because linear programming theory tells us that the maximum or minimum, the optimum values, must occur at one of these corner points. So let's look at the process for linear programming. You're really going to need to focus on this process and almost use it like a checklist step by step. So first we have to understand the situation. We define the variables, the constraints, and the objective function itself. The variables should be common to both the constraints, which are inequalities, and the objective function, which is an equation. We will then graph the constraints, only the constraints, as a system of linear inequalities. If you need some help in that, go ahead and go to some of the previous screencasts which teach you how to plot linear inequality systems and then how to solve them graphically. Then the critical part of this is that feasible region, which is the polygon formed by the system of constraints, has corner points or vertices. We need to determine those. If you've done a good job graphing very carefully, you can do that graphically. Otherwise, you're going to have to find the corner points through the intersections of the appropriate lines. And then we're going to test those corner points against the objective function. This is the only time the objective function is actually used at the end to test the corner points. And we're going to pick the corner point that's going to give us the best, the optimum value. It may be a situation where we're trying to maximize something, in which case we're looking for the largest quantity. If it's minimizing, it's the opposite. We're looking for the smallest. It's important to pick the one that's appropriate for the situation we're using. Let's go ahead and do a linear programming problem involving a landscaping company. So typically these problems have a lot of information to sort through, but if you follow the process, it'll work. The landscaping company has crews that mow lawns and prune shrubbery. So we got to look as we're going through this, what are the things we're trying to quantify? And the company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. That's how much time it takes to do each of the jobs. Each crew is scheduled to work no more than 2 pruning jobs a day. Each crew's schedule is set up for a maximum of 9 hours per day. And on average, the charge for mowing a lawn is $40, and for pruning shrubbery, it's $120. And we're tasked with finding a combination of mowing and pruning that will maximize the income the company makes in one day for one of its crews. This is what linear programming is about, maximizing or minimizing. In this case, we want to maximize income. So let's take all of this information and put it together. So step 1, define the variables, the objective function, and the constraints. Well, the variables are mowing hours and pruning hours. This is what we're in control of as the company. We can decide how many mowing hours and how many pruning hours each of our crews gets. What results is the income, and that leads directly to our objective function, which we are trying to maximize. We're in business, we're trying to make money. That involves making as much money as possible. So the income I is equal to 40 times M, because mowing gets us $40 an hour, plus 120 times P, pruning gives us $120 an hour. That's what we're trying to maximize. That's the key to the whole thing. Interestingly enough, though, we don't graph that. We have to graph the constraints. The constraints are what bind us to the situation. Well, we're limited by a 9-hour day. The crew can only work a total of 9 hours. So the total of mowing and pruning, each of which take 1 hour and 3 hours a job respectively, must be less than or equal to 9. So 1 times M plus 3 times P has to be less than or equal to 9. That's our first constraint. The second major constraint is we're limited to only 2 pruning jobs a day. So no more than 2 pruning jobs means that basically the number of prunings, which is P, has to be less than or equal to 2. So that's our second major constraint. Since mowing and pruning jobs are the things we're in control of, it's not explicitly stated, but in most of these problems, we're only in quadrant 1. We're only dealing with positive values. So we need to include that the number of mowings has to be greater than or equal to 0, and the number of prunings greater than or equal to 0. Obviously, we can't have something in the negative in one of these factors. So next we graph these constraints as a system of linear inequalities. So we need to draw ourselves a graph, and I've chosen to put the mowing on the horizontal axis and the pruning on the vertical axis. And I'm going from basically 0 to 10 hours for each, although that's probably a bit much. So I've got my 4 constraints. We're going to graph them one at a time. First thing we'll look at is the 9-hour day. It is given by 1m plus 3p less than or equal to 9. So our horizontal intercept is at 9. Our vertical intercept is at 3. That line, and I'm going to do everything in quadrant 1, which will take care of these last 2 constraints. That line is the boundary of the 9-hour day. We need to test 0, 0, and since 0 is less than or equal to 9, this lower portion of the triangle is in fact the region that's feasible for the 9-hour day. So the next constraint we're going to look at is the limit of pruning, the 2 prune limit, if you will, and that is a horizontal line going through the intercept P equals 2. Now it's less than or equal to, and of course if we tested 0, 0, we would get 0 less than 2, meaning that below that is the region we're talking about. So we need to look at the area they have in common, and in fact, that is this purple region here, this trapezoidal region in this case, is the feasible region for our situation. Now let's determine the corner points of this feasible region, and they represent the vertices of this trapezoid that's in purple. And our maximum and minimum must occur at one of these points. The first point is 0, 0. 0, 2 is a corner point up here on the upper left. 3, 2, 3 mowing, 2 pruning jobs is that upper right point. And finally, 9 mowings and 0 prunings is the far right corner. So now let's take those 4 corner points and test them against the objective function income equals $40 times mowing plus $120 times prunings. So we take the first point 0, 0, and it yields kind of what we expect. If we go 0 mowings and 0 prunings, we're going to make $0. That's the minimum, not what we're looking for here. We can test the point 0, 2, the second corner point. 40 times 0 plus 120 times 2 is $240. If we test 3, 2, we get 40 times 3 plus 120 times 2 equals $360. And if we test the final corner point, 9, 0, we get 40 times 9 plus 120 times 0 is $360. So the conclusion is actually both of these last corner points are acceptable maximums. Either 3 mowings plus 2 pruning jobs or just 9 mowing jobs both maximize our income for the crew for the day. That's how linear programming works. In this screencast, we learned about linear programming, which helps us optimize situations.